Okay, thank you, everyone. So good afternoon. This is our fourth of our 60th anniversary commemorative series talks, and today we're excited to have with us Dina Katabi from Massachusetts Institute of Technology. She's a professor in computer science, artificial intelligence laboratory, and leads the NEMIT network group at MIT. Is that correct? And so recently, she was a recipient of a Faculty Research Innovation Fellowship and has also received the SIGCOMM Best Paper Award. And I understand there's lots of press about some of her recent work in FFT, which maybe she'll talk to us about today. Her primary goal of her research is to build new protocols and architectures that improve the robustness and performance of computer networks. She's working on wireless networks, network security, traffic engineering, congestion control, and routing. And additionally, she draws on advanced mathematic models to deliver practical network solutions. With that, I'd like to thank Dina for coming today and joining us, and we're looking forward to your talk, and thanks a lot.
Thank you. So thank you all for being here. So I'm sorry, it's a bit crazy. Like, I just arrived today in the morning, and I'm going to talk about wireless networks, but as you can see, I'm all wired and connected. Yeah, and like just arrived, like we had this nice result about making FFT, the discrete Fourier transform, faster. So I'm not going to talk about this, but Bob told me that some of you might be interested in asking a question about that, so I can take the questions after the talk. So what I'm going to talk about today is wireless networks, as I said, because I think there's so much that is changing about how we perceive wireless networks, how we study them, and how we advance the state of the art in wireless networks. And this is my area that I'm very much interested in. And I want to tell you how the last 5 years have changed completely the way we address wireless networks. So the problems that I'm going to talk about is how do we improve the throughput and reliability of wireless networks. Okay? And the approach that we are going to adopt throughout this talk is to cut across the layers of the network stack. Now, what does that mean, to cut across the layers of the network stack? So basically, if you look at how wireless networks have evolved, they inherited a lot of things, many things, from the internet, from the wide internet. And in the internet, you divide the network stack into isolated layers. At the bottom, there is a physical layer, which is in the business of taking signals and spitting out correct packets. Now, then there are networks and higher layers who take these correct packets and route them toward the destination to deliver a service. So this model of layer separation has worked great for the internet. And at the beginning, actually, it worked also great for wireless networks because it allows them to inherit routing and forwarding from the internet. But as wireless became more popular and more congested, this model stopped working well. And the reason is that wireless actually is different. The physical layer in wireless networks has so much more errors than in the internet. In the internet, you have a cable. You hardly have any errors. In wireless, you have orders of magnitude more errors. So if you insist that the physical layer can only deliver to the network correct packets, then you're going to end up in a situation where you are sitting there as a physical layer. You take a packet. Oh, it's not correct. You toss it away. Not correct, toss it away, until eventually some packet is correct and you deliver it. So you get excessive losses inside your network and inefficiencies. So what we're going to talk about is a new approach that does not take this isolated layers, but it is a cross-layer design which exploits the interaction at the physical layer to deliver better performance at the network and higher layers. So throughout this talk and the rest of this talk, I'm going to tell you about this cross-layer design. And we are going to go across all of the layers. Now, some of you may not have these layers, but these are the layers of the network stack. So we're going to go over them and see how this new design can integrate them together. And as I do this, I'm going to tell you to describe to you multiple examples. So the first one is the first Wi-Fi receiver that can decode collisions. Collisions are packets that suffered interference. So we can, if we adopt this view of cross-layer design, we can actually decode interference. So the second thing that I'm going to tell you about is something called analog network coding, which is in your design that actually exploit interference. And finally, I'm going to tell you how you can design robust mobile video if you adopt this approach. So let me start with the Wi-Fi receiver that can decode collisions. And I'm going to start integrating stuff from the bottom. So we're going to start by integrating these two layers and provide a cross-layer design across the physical layer. This stands for physical layer signal. And this is the medium axis, like how you transmit stuff on the wireless medium. So let me start by reminding you guys how Wi-Fi 802.11 works. So the way it works, actually, is fairly simple. The wireless medium is a broadcast medium. It's like the Zoom. So if some node speaks on the medium, everyone hears. And the way this works is that every node listens on the medium. And if nobody else is transmitting, it doesn't hear anyone else, then it can go ahead and transmit. So if you have two transmitters, Alice and Bob, then they're going to apply this. So they're going to listen on the medium. They will hear that the medium is idle. So one of them will start first, say Alice. And then Bob will hear Alice's packet and will start after the packet ends and will transmit his packet. So if everything is working perfectly, Alice and Bob will go one after the other. We'll hear each other, we'll go one after the other. Now, this if everything is working perfectly. In wireless, nothing works perfectly. So there is a classic problem called the hidden terminal problem, which happens when you have some obstruction between Alice and Bob, so they don't hear each other perfectly. So what happens now is that because they don't hear each other, they might transmit at the same time, creating what's called collision. So now the access point the router cannot hear, cannot decode. It can hear signal but cannot decode this collision. So now what these guys are going to do, what the protocol says, is that jitter your transmission and retransmit the same two packets. So they retransmit the same packet, but again, they overlap in time and again a collision because they can't hear each other. So they keep jittering their packets and retransmitting the same packet, getting collision after collision, until eventually this jittering actually gives you enough spacing between the packets that some packets get through. But what happens in this case is that despite that eventually some packets get through, you get very high loss rate that no application works. So the question that we ask, can we do better? So in fact, can we take a collision of Alice's packet and Bob's packet and the retransmission of the same two packets that also collided and decode the two original packets? If we can do that, then as if the collision did not happen, and as if things were perfect, Alice and Bob transmitted one after the other. Okay? So if we can do this, then we solve the hidden terminal problem. So let's see how we can do it. We're going to exploit that senders are typically not synchronized, because just in practice, unless you try very hard to synchronize them, they are not synchronized. So which means that if you have two collisions, there will be some offset, like Bob's packet is going to start after Alice's packet by some offset, and the same some offset in the second collision. Which means that there are going to be some bits that are interference-free in both collisions. So we're going to leverage these bits to decode. So we're going to leverage these interference-free bits to decode. Here is our decoder, which we call zigzag decoding. So as I said, there is this offset, delta 1 and delta 2. And because it's random, it's very unlikely that it's going to be the same. Which means that actually you can always find a chunk of bits that are interference-free in one collision and that have interfered in the other collision, like chunk 1 here. So notice chunk 1 is interference-free in the first collision and has suffered from some interference in the second collision. Now, because chunk 1 is interference-free in this first collision, we can just decode it using standard methods. Once we decode it, we can go ahead and subtract it from the second collision. And now we have chunk 2, which become interference-free. So we can decode it using the standard methods. So now we subtract it from the first collision. You get chunk 3 that is interference-free. You can decode using standard method. And you can go ahead doing this chunk after chunk until eventually you decoded both packets. So that was actually the first receiver design that can decode collisions. And the reason why we can do this is by understanding what was happening in the physical layer. Now, of course, so this is what we did. We delivered 2 packets in 2 time slots, and yes, we solved the hidden terminal problem. But, I mean, of course, it's not that simple. Like, what does it mean to subtract packets and bits and stuff like that? I mean, are we subtracting, in what field are we subtracting? Are we subtracting in the finite field? Are we subtracting in the real signals? What are we subtracting? So let's try to get closer to what we are doing here. So you really have a signal. And this is what the access point is going to receive. And the first thing that you have to answer, is it really a collision? And if it's a collision, then what is this offset delta? How do I know where the offset delta is? So here's what we're going to leverage. So say this is the signal that we received. Now, we know that every single packet starts with a known preamble. This is known to the whole world. This is part of the protocol. So the access point knows this preamble. So what the access point can do is to correlate the known preamble with the preamble in the signal. So it starts at the beginning of the signal, sample by sample, correlating this as a function of time. Now, just by the pure fact of how correlation works, you're going to get 2 spikes that align exactly where the preamble in the signal is. So here's what we did. We actually discovered that this is collision. And also, we discovered the offset, the exact offset that we needed. And this is based on this preamble correlation. Now, some of you might be wondering, OK, so it's fairly easy to understand that this spike exists here because there is no interference. But here, there is interference from the body of the pink packet. So how come we still can get the spike? This is just a simple property of correlation. Correlation with independent signal is 0. So the body of the pink packet, as if it doesn't exist, because it is independent from the preamble that we are correlating with. OK? So great. So now we know that it is a collision. We know the delta. So we can go ahead and subtract. But how do we subtract a chunk of bits? What does that mean? So of course, you cannot simply take a signal from one collision and subtract it from the other collision. That's meaningless. And the reason why it's meaningless, because the channel may have changed between the 2 collisions. So say, for example, this is Alice's signal in the first time these 2 packets collided. And this is Alice's signal in the second time they collided. The channel might have changed, so the attenuation of Alice's signal has changed. The channel has a phase, so the angle of Alice's signal may have changed. Also, this is a digital system, so you don't have a continuous signal, really. You have samples of your signal, and you may be sampling at different times. So you cannot just take these samples and subtract them, thinking that they are the same as the samples in the first collision. So I'm going to describe the solution at a very high level. And conceptually, obviously, the details are in our paper. So here's the solution at a very high level. So what can you do? How can you subtract these chunks? So the first thing that you have to do is to decode the chunk from the signal domain, bring it back to the bits. OK? So now, by taking the signal and decoding it into bits, you remove the effect of the channel during the first collision. Now, you take these bits and you remodulate them, creating a signal that is that is channel-free, a signal that hasn't gone through any channel. And now, to this signal that is channel-free, you apply the effect of the channel during the second collision. And now you got something that looks exactly as if it did go through the second collision. And now you can subtract it. Now, does this generalize? I showed you just 2 packets colliding and with very like toy example. So let's see. So what happens if I flip the order? If like Bob's packet starts before Alice's packet in the second collision? Like the blue packet here starts before the pink packet in the second collision. Does it work? What do you guys think? Yes, it does work. Because, I mean, the only thing that it needs is a chunk of packets that are interference-free in one collision and have suffered interference in the other. And chunk 1 is still valid here. Packets have different sizes. Well, no problem. Of course it works. Actually, it's easier. You can now find many chunks that are collision-free in one, interference-free in one collision and have suffered interference. What if we have many packets that are colliding? Actually, it still works. Because conceptually, the way you should think about this system is like linear equations with unknowns. So the channel, all that it does to you is that it linearly combines the signal. So you can think of collisions like linear equations. And there are linear equations over the unknowns, which are the packets. So as long as you have as many linear equations, as many collisions, as there are the unknown packets, then you can decode with the system. OK? So of course, there are so much details about actually making it work. But I just want to show you that this is not just conceptual thing. You can actually take these concepts and then make them work. So we implemented these concepts using software radios. We use the USRP hardware, GNU Radio software radio, and the 2.4 gigahertz, which is the same as Wi-Fi. And we have this test bed. And here, the red dots are the nodes. And we picked a test bed that kind of like similar to what you would expect in reality. So 10% of the nodes are hidden terminal. They can't hear each other. And 10% of the node pairs can hear each other every now and then. So they are partially hidden terminal. And then 80% of the node can hear each other perfectly. So this is like a real network, something that works most of the time. Sometimes people are in dead spot. They interfere with each other. They can't transmit. But most of the time, it works. And we repeat these experiments. In each run randomly, we pick a node to be the access point and 2 nodes to be Alice and Bob. And we create something very similar to the setup I showed you. So here are the results. So what I'm plotting here for you is a CDF, is a cumulative distribution function of the throughput inside the network normalized by the rate of the radio. Let me show you 822.11. So here's 822.11. There is 10% of the nodes, as you can see, 10% of the node pairs, they get 0 throughput, which was what we expect based on the topology that we were talking about. There are another 10% that get suboptimal throughput. And about 80% of the node pairs perfectly sense each other, so they get the nominal throughput of the radio. Here are the results for zigzag. So the first thing that you should notice is that there are no hidden terminals that are losing their throughput. Everyone gets at least the nominal throughput of the radio. OK, so we eliminated the bad effect of hidden terminal. Now, when we actually first got these results, we were surprised because at some point, like for this part of the results, we achieved better than if things did not collide at all. Not just we solved the collision problem, the throughput is larger than the nominal throughput of the radio than if you just sent one after the other. Can you guys guess why? So it's actually something called temporal diversity. It's basically, now you have each packet appears on the channel twice. So it's very unlikely that in both times when it appears on the channel, the same bit is impacted by high noise. So this property is called in wireless temporal diversity. And actually, it turns out that it's better to let these packets collide. You can get even higher throughput. So in fact, overall, the throughput in this network has improved by 25%. But what is really interesting is really the hidden terminal problem, because we all know that when we are in a dead spot and we can't really get our stuff through, this is when we get really annoyed. And for those nodes, we reduce the loss rate from 72% to 0.7%. So effectively, we transformed links that were completely useless into perfectly operational. Okay? So I'm going to move to the next example, but before doing this, any questions?
Are wireless dead spots places where you can't get signal, or are the wireless dead spots places where there's high
Both.
or high interference?
Both. Basically, you can't get things decoded. In many cases, it's because you can't get the signal. In other cases, if somebody else, you can get a hidden terminal problem. I think this is particularly true. You get a lot of hidden terminal in DARPA managed outdoors because like the environment is not symmetric.
What's the minimum part of a free packet that you can use to actually decode it?
What is the minimum?
Can you use a single bit?
Actually, this is very interesting. No, actually, you can't use a single bit because obviously there are dependencies that you have to. So you actually need a minimum at least of O of the M symbol. So these are used O of the M internally, and you need a bit more than that. So yeah, so that's definitely true. But the nice thing is that the protocol internally introduces these jitters, and that gives you more than enough at the beginning. That it's very unlikely actually that the separation is just few bits. Yeah. So now let's move on to this thing called analog network coding. So what I want to do now is to go one layer up in the stack, which is the routing layer, and see how we can now integrate all of this and what does it mean for us. So we're going to go back to our friends Alice and Bob. But we are going to change the experiment a bit. So instead of Alice and Bob sending both to the access point, now Alice and Bob are sending to each other. So in the current system, like if two people want to send to each other, Alice's packet will go to the access point and will forward the packet to Bob, and Bob's packet will go to the access point, and the access point forwards the packet to Alice. So imagine a scenario where actually they are relatively far from each other that the radio range does not reach directly. So you need this help of the middle guy. So if you notice what happened just now, to exchange a couple of packets between Alice and Bob, we used 4 wireless transmission, 4 times slots on the medium, just to exchange a couple of packets. Can we do better than that? What do you guys think? Sure. Okay, sure. Good. Okay, so I just give you this like introduction with zigzag. Maybe we can use zigzag to do something better. So let's see what we can do. Here is a naive way, actually, of applying zigzag. So let's say Alice and Bob transmit their packets at the same time, and you get a collision at the access point. Now, we know that we need 2 collisions, because this is like linear equations and unknown. So we're going to get a second collision. And now the access point can decode the collisions and forward Bob's packet to Alice, Alice's packet to Bob. Is this any better? No. This is, again, 4 time slots on the medium. So naively applying zigzag doesn't help you. OK, so but who said that the access point actually has to decode the packet? Really what you care about is that the end system, Alice and Bob, being able to get each other's packets and each other's signal. The access point is just an intermediary, so you don't really care about the access point decoding. So what if the access point does not decode? So here's a different approach. Alice and Bob simultaneously transmit their packet to the access point. This is like 2 people shouting in both ears. You really can't hear anything. And we can even prove it that the amount of information exceeds the capacity. There is no way this access point can decode the packet. But as we said, it doesn't really need to decode the packet. This access point can amplify and forward the signal. And now, because this is a broadcast medium, both Alice and Bob hear this collision signal. Alice just transmitted her packet. She has it, so she can use it as this chunk that is interference-free in one collision and has interfered in the other, and subtracted using zigzag from the collision and obtains Bob's packet. Bob can do exactly the same thing to obtain Alice's packet. So what did we do here? We actually used just 2 transmission, 2 time slot on the wireless, on the shared wireless medium, which is the most important resource in any wireless network, just 2 time slots to transmit exactly the same amount of information. 1 time slot from both Alice and Bob to the router, and another time slot from the router to both Alice and Bob. So we basically doubled the throughput. So one thing that makes this interesting is not just we double the throughput. This is conceptually actually is very interesting, because this actually extends a very beautiful theory called network coding to the signal domain. So network coding is a theory that tells you that where you have the routers creating linear combinations over the finite field of the packets themselves. Okay? So this is what network coding tells you. Now, what this new scheme tells you is that the channel itself, if you transmit signals at the same time, the channel itself creates linear combinations over the real field of signals, as opposed to linear combination of a finite field of the bits inside the packet. So this is an extension of the network coding theory, and this is what we call analog network coding. And you can show that it applies to scenarios where the traditional theory could not be applied. So let's see whether it actually works in practice. So what we did is implemented this stuff, and I'm going to show you results with the following metric. So we're going to look at the throughput with analog network coding divided by the throughput without analog network coding with traditional routing in the same example that we just saw, which is the Alice-Bob scenario. Okay, I have to make sure that I don't trip. OK, here are the results. So again, this is a CDF. This is distributed cumulative function of the throughput gain. And you can see that the median gain is 1.7, which means that we gain about 70% improvement in our throughput. So this is less than doubling, obviously, because in practice you have some inefficiency and some additional errors that you have to deal with. But this is pretty good. We are pretty close to doubling. And actually, this doubling is only for this simple scenario that I showed you. But you can show that in other scenarios, the same theory, if this analog network coding, can get you much higher gains. OK. So now we went through 3 layers. Can we go 1 layer up and go to the application? So I'm going to tell you how we can start looking at the application and the physical signal, the whole network stack together. And to do that, I'm going to show you in the context of robust mobile video. So we're going to change gear and now look at video. And we all know video is the next killer apps, according to all predictions. You can ask whoever you want in the industry. Now, we are all very much excited about getting all TV programs on our handheld devices, all concerts live, and sporting events on our tablets or cell phone. And this is exciting future that we are looking at. But we also all know that mobile video doesn't really work that well. And anyone who tried mobile video on their iPhone knows that for sure. So mobile video today suffers from glitches and stalls. So how can we solve this problem? But before talking about how to solve the problem, let us try to understand a bit where the problem comes from. The problem actually is very natural. Mobility causes unpredictable variations in your channel. So if this is your sender, and this is your receiver, this is how the channel typically looks like. So you can see this is a channel quality, SNR, as a function of time. And you can see all these ups and down in the channel over very short time scales that are about milliseconds. In fact, guys, if I just do this, the channel just goes crazy. So no wonder that video actually doesn't work, because video cannot deal with channel variations that well. This causes a non-technical problem we refer to as the performance cliff. And it means that if you plot video performance as a function of your channel quality, you're going to see a cliff point. You're going to see a particular channel quality here, that if your SNR improves, your video does not improve. And if your channel quality goes below that, your video stops working. It becomes unwatchable, becomes garbage, really. Okay? So this is actually why your video glitches and stalls, because basically, if the channel quality decreases a bit, then you fall off the cliff. And if you fall and the channel comes back, then you go back to the cliff, and that would be a glitch. However, if the channel changes and degrades and you fall off the cliff, and if it stays bad for a few minutes, then it will be a stall. Okay? Now, I'm sure multiple of you might say, oh, but you know what? You can use like error correction code. You can use FEC. You can change the modulation, add redundancy to your video, do something. And all of that is true. Yeah, you can change the modulation. You can add forward error correction. You can do all that. It gives you a different cliff point. So this is for H.264, which is state-of-the-art video codec, with different modulation and code rate. And I can plot for you the different graphs for a variety of modulation and code rates. In fact, for all the modulation and code rates that you have with Wi-Fi and WiMAX channel-like. So you're going to have a different cliff point for a different coding and for different modulation. And you can pick which one you like better the blue line or the yellow line. But you're going to always live on this cliff. Any question? Do you guys like the cliffs? Yeah, exactly. You can fall easily off the cliff. So what is the ideal scenario? This is what you really want. If you are to pick, that's what you want. You want basically at any point, at any channel quality, you want to get the best video for that channel. So for whatever your channel quality is, like pick your point, you're going to get the best possible video performance for that channel quality. This is the ideal scenario. There'll be no cliffs. Things will degrade smoothly if the channel degrades, will improve smoothly if the channel improves, and at any point in time, they are the best possible for that channel. Okay? And if we can get this, obviously, there will be no glitches and stalls. So before I can tell you how we can try to get into this ideal mode, let us try to understand a bit where these cliff points coming from in current video. So today's video why today's video suffers from cliff point? Today's video has two components: the video codec, which compresses the video, and the channel code, which protects the video as you transmit it over the erroneous wireless channel. Now the problem is that both video coding, the compression, and the error protection code take real number pixel values and transforms them into sequences of bits. So they move from the real field into the finite binary field. Okay? Now, this is problematic because they destroy the numerical properties of these pixel values. So if you take a sequence of bits like 1110 and 111, and it's just like one bit flip from each other, they might refer to completely different pixel values, so 5 and 149. So that one bit flip can completely change the pixel luminance. But the actual problem is much, much worse than that. So I'm sure that many of you guys, or maybe all of you, know about Huffman coding, entropy coding. I mean, this is a term that's familiar. So entropy coding is underlying all of today's video codecs. And entropy coding is a variable length code. Like the code word has variable size. And if you get a bit flip, then the receiver doesn't know how to sync with the code word. So it doesn't know where actually the next code word starts and where it ends. And as a result, you lose synchronization between the transmitter and receiver. So actually, one bit flip can render everything at the receiver to be garbage. So today, we have a video at the receiver where if you can correct all the errors at the receiver, you get perfect video. You get a video that looks exactly like it was at the transmitter. But if after decoding, there is one residual bit error, then you can get arbitrary errors in your video at the receiver, and which is a cliff point. But we had a video that didn't have cliff effect. Do you guys remember those old good days? Do you know of a video that did not suffer from cliff effect? Analog TV, yes. Analog TV actually did not have the cliff effect. Now, analog TV is bad. I'm not saying that we should go back to analog TV. There was a very good reason that we moved away from analog TV. It's extremely inefficient, and I'm not saying we should go back to analog TV. But analog TV got one thing right, which is that it didn't have a cliff effect. It used to be that if the channel gets bad, you start seeing noisy pictures, but you never see this blue screen of death with analog TV, which I see a lot with my laptop. I hope we will not see it today. OK, so what was the thing that can we just get the best of analog TV? Can we get the smooth degradation of analog TV, but avoid all the bad things that we try to move to digital TV so that we can avoid them? So let's see whether we can get the best of analog TV while avoiding the worst part of it. So analog TV did not suffer a cliff effect because it did not take real numbers and transform them into bits. It actually took these real numbers and scaled them up and down and transmitted them on the channel. So it didn't change from the real field to the finite field. It just took a real field and transmitted as a signal. And as a result, there was a linear relation between what was transmitted on the channel and the pixel luminance. Now, because of that linearity between the two, when you get small perturbation on the channel that affect your signal, it transforms into small perturbation in the pixel luminance. So you don't get a cliff effect. But analog TV was no good because it's completely inefficient. Come on, I mean, it did not compress the video. And that's like a no-brainer. And also, it did not have error protection for transmission on the channel. So what I'm going to show you here is a new system we call Softcast, which has the best of both worlds. Like digital TV, it is efficient. But like analog TV, it has no cliff effect. So how does it work? So instead of having two components, one for compression, one for error protection, let's just take one code that both compresses the video and protects it from errors. Now, the key property of this code is that it has to be linear. Because if the code is linear, then small perturbation in the signal on the channel translate into small perturbation in the pixel luminance, and you don't get a cliff effect. So good? Are you happy with this system? Shouldn't be happy yet. I just got you back analog TV. Come on. So this on its own is useless unless actually we can keep linearity of the code, but compress and protect from errors. If we can do that, then we combine the best of both worlds. OK? So now the first challenge is that existing compression schemes are not linear. They're going to screw up the linearity for us. So here's what we're going to do. We're going to compress by dropping three-dimensional frequencies. What do I mean by this? So if you look at sequences of frames in a video, then we know that the pixel luminance changes slowly, both in space and in time. Which means that if you move the video to the frequency domain, the high frequencies, the high spatial and temporal frequencies are going to be 0 or close to 0 because everything is moving gradually. So this is exactly what we are going to exploit. So in Softcast, we transform the video to the frequency domain using three-dimensional DCT. So for people who don't know what DCT is, just think of it as FFT. So this is actually exactly what happens if you take these exact 4 frames and transform them to the frequency domain using 3D DCT. Here, the gray level is the magnitude of that frequency. So as you can see, so many points are black. They are zeros. They have no energy. They have no information. So there is no point transmitting them. So you can compress this video by simply dropping all the zero frequencies. That will give you lossless compression. And you can even get any level of compression, lossy compression, by dropping all the frequencies that are below certain threshold. So you can give you any level of compression. So note what we did. So 3D DCT compresses both within a frame and across frames. So it gives you really intra-frame and inter-frame compression. And it is linear. So now we have what we want, linear compression scheme. Any question? So there is the typical question that everyone asks here. Is this better compression scheme than MPEG? What do you guys think? No, actually. That's the wrong message to take from the start. This is not a better compression, 3D DCT. So this is what 3D DCT is, but it's not a better compression scheme than MPEG 4x10 or the best compression schemes that we have now. The problem is what we have now is that we have these video codecs which are perfect in terms of compression. They are really good. But if you look at how they evolved from compressing video to put it on DVD and CDs. They are not for erroneous wireless channels. They assume there are no errors. So they are very fragile for errors. So now what you do, you take this video, you compress it with your best codec, and it is small. It is effectively like really compressed, perfect compression. But you take that video and you want to put it on the wireless channel which has errors. So what do? You add redundancy. You add error correcting codes, and you add redundancy in a variety of forms. And again, the video is blowing up. And now you put it on the wireless channel because otherwise it's just going to die immediately. And you don't win. So what 3D DCT is a slightly worse compression than the existing system, but like 10%. And however, it's very resilient for wireless errors because it's linear. It's a linear operator. So small noise just causes small noise in your video, as opposed to completely everything breaking. The problem is that we took something that was designed originally for DVD and CDs, and without trying to we are just tweaking it here and there, and we put it on a wireless channel. It wasn't designed for that. OK, so now the second challenge is that existing error correction code and error protection code operate over bits. They don't operate over the real field. And therefore, they are going to destroy our linear property if we just use them as they are. So here's our solution. We're going to protect the transmitted signal by magnitude scaling. This is best understood through an example. So let's take, for example, say this is the DCT value at the output of the DCT compression step. Now, before transmitting it on the wireless channel, we're going to scale it up 10 times. Now, the wireless channel will add some noise, let's say plus minus 0.1. And you receive this value as the receiver. And the receiver has to scale it down 10 times because it was originally scaled up. So you get this value. But note what happens. By scaling up before transmission, reduced the OK. I guess this is exactly what I should have expected. See, this is the value of wireless. If you had wireless, you wouldn't have to I don't have to walk with a wire and worry about my mic. But at least I haven't tripped on it yet, so that's good. OK, but basically scaling up the magnitude before transmission, at the receiver, you have to scale down. But the effect is that you scaled the noise on the channel 10 times. OK? So effectively, scaling up before transmission reduces the noise at your receiver by the same factor. So great, let's scale up everything before transmission. We'll have no noise, we have no problem, wireless will be perfect. There's something wrong here. Obviously, you can't scale up everything because basically when you scale some value up and you transmit it on the channel, the magnitude is going to be larger and will consume more power. And your hardware have certain power budget. So you have to be smart in what you scale up, what you scale down. So what you can do is to formalize this problem as an optimization problem. It's a linear optimization problem. Basically, what you want is to find the optimal scaling factor such that your error at the receiver is minimized, subject to linearity of your code. And I'm not going to go through the exact solution, which you can find in our paper, but intuitively, it is as follows. So basically, think of it this way. So you want to put your power where the information is. But how do you measure information? How do we measure information? Entropy. Entropy is a measure of information. And another way to measure information is also the variance of the signal, which is very much related to the entropy. So basically, all that the theorem is saying is that we are going to scale these DCT values according to their variance. And because the variance is how much information they have, and that is where you have to put the power. And it formalizes it in a manner that finds the optimal scaling. So what we got so far is magnitude scaling is linear, and so you have linear error protection code. So fine. So now actually we got what we want. We want a system where we can have a linear code so that we have smooth behavior, and we want compression, we want error protection, we got it. So let's see whether it works in practice. So here are empirical results. Again, this is implemented with software radios, and it's USRP hardware, GNU radio software radio package, carrier frequency 2.4, which is the same as Wi-Fi, and OFDM-based physical layer. OFDM, if you guys haven't heard of it, is just the modern transmission system used in Wi-Fi, WiMAX, and LTE. So we are going to compare three systems. We're going to compare softcast against the existing approach, which uses state-of-the-art video codec, H.264, over Wi-Fi, WiMAX-like channel based on OFDM. And we're going to also compare against a third approach, which is layered video. Like I'm sure many of you guys have heard about layered video. Layered video is like you take your video, you divide it into base layer that is necessary for all receivers, and then enhancement that improves the quality of the video and that receivers with good channel can obtain to improve the video quality. And some people refer to layered video as scalable video coding, SVC. So here are the results. On the x-axis, the channel quality. On the y-axis is the video quality. So this is very much the same metric that we were looking at before. And here's the existing approach. Actually, these are the same graphs that I showed you at the beginning. These were from actual empirical results on actual wireless channels. Here's softcast. So it's not exactly the ideal, but it's pretty close. It's not the ideal because you can see at some point this is slightly below these curves, like about 1 dB, 1.5 dB. But it's pretty smooth. It's very smooth and very close to ideal. There is no feedback whatsoever. There is no adaptation from the receiver side. It's only the code at the transmitter. The transmitter codes the stuff using softcast, and the receiver is sitting there just collecting these signals on the wireless medium, and it just works producing this graph. OK, so it gives you smooth degradation. Now, how about layered video? Here's two-layer video. It transforms this single cliff into two smaller cliffs. But it also loses efficiency as it does so. And you can prove that actually, if you want to divide your video or any source signal into two layers, you're going to lose efficiency, typically about 20% of your efficiency. OK, so I just want to show you visually how it performs. Because in video, typically, you really want to see the visual effects. So we use this video, which is a typical video that people compare against traditionally. So it's like it's an old game, but it's like we use it because People for the last 10, 15 years have been comparing against this video. And in this example, what we have here is our tower, the transmitter, and this is the mobile device, is the receiver. And we are going to see what happens to the video as the receiver, the mobile phone, moves away from the tower. And we are comparing two things, H.264, MPEG 4 part 10 against the new approach softcast. If you look at what's happening here, so let's go back. When the channel was good, both videos were good. However, what happens here is that the channel went through like small glitch, like very, very small change in the SNR. And you can see the glitch in the other video. And if you read the SNR value under the mobile phone, so see how the difference in SNR between the good channel and the glitch is just like fraction of a dB. It's really small, which tells you how fragile today's video is. Now, as you let this go on, eventually this guy just stalls. Because this is actually is doing what any decent video coder does, which is basically once it doesn't have, the signal becomes completely meaningless, it just keeps the last frame that was able to decode. While the other guy, you can see you can completely watch your game. And even as the SNR goes down to 4 dB, which is pretty low SNR. And as you can see, like as the SNR is going down, the channel is getting more noisy. But that's something that you can tolerate with your video, with your mobile device, as opposed to just like completely stopping. So with this, actually, let me go back. And of course, we build on a lot of foundational related work, both in like system networks and information theory and video coding. But the difference, the real difference, is that the traditional approach in all of these systems is just to work within a layer. The video codec people just do video. And this is why we get a problem when we try to put it on a wireless network. And the information theorists just look at codes, but they don't look at, OK, so how it's going to perform in practice, and how does it integrate with the application. The networking people traditionally just don't worry about the physical signal at all. They just assume correct packets. But once you integrate all of these things together, you can get much, much better performance. And this is really where the future of wireless is moving. So let me conclude. So the old approach is to do layered network design, optimize within a layer. Now the new brave word is to optimize across the layer. And if you can do this, then you can decode collision packets that have interference. You can exploit collision. You can exploit interference to get higher throughput using things like analog network coding. And you can build robust mobile video that doesn't glitch or stall. And with this, I'll stop and take any questions.
So are there any questions for Dean?
Is there a role for stochastic resonance in any of this?
So stochastic resonance actually has a very direct role with some other stuff that I'm doing recently. So when I started, was talking about this new stuff that we did on fast FFT, faster than doing the current FFT. And resonance is very much one application where you are looking for resonance of like a variety of, like you can apply it in medicine and bio and all that stuff. So that actually direct application. I'm very happy to talk in details about that.
So I have that same problem with the robust mobile video. What's the adoption technique for this then? So would the carriers have to adopt the softcast, or is there another methodology that you could put in place?
So basically, what you need to change what we currently do. So the carrier have to, I mean, if you want to do it over cellular, then the carriers have to adopt it. But the way I think about it is that what is nice about starting with, for example, with the Army is that you have a niche scenario where you can prove that actually it has a lot of benefit, and then you can integrate it with the carrier network. There will be there is enough business for video that people will do it if they start seeing benefits. So basically start with a domain that is where you can deploy it on both ends, and then move to a domain where the carriers have to deploy it.
So I know that you often get these problems with wired video as well, not just wireless. Is that a different mechanism, or is it the same?
So actually, yeah, you get similar problems with wired video. They are way less than wireless. They are, in principle, very similar. I mean, basically, any loss that you have in video, it's just the video is very much incapable of dealing with. So in principle, they are similar. In magnitude, they are way, way less than what you get over wireless.
Okay. So in the context of the applications that ride on these infrastructures, maybe like our cloud applications, in the context of putting all of those sort of lower layer decoding and sort of unified layer strategies together, how will this make the software itself, not just the video, but literally the applications themselves function better? I mean, you see like a strategy for getting to the software itself as a...
Yeah, very much, because basically, let's say that what you have is, just take a very, very simple example. So handoff. I mean, basically, let's say that I want to use the cloud and move with my video inside this whole building and being able to hand off from one access point to another access point and run all of the complex, maybe even I'm doing pattern recognition and detecting objects and stuff like that on the cloud and just transmitting stuff. So if you do it today, it's very, very tough, because basically as you move across from one transmitter to another transmitter, the first transmitter doesn't know what the other transmitter has already delivered to you. So their information is not complementary. And while if you move to these soft systems, it doesn't really matter. Like, you just think of packet in the system as it's like water. Like you are having a basket and you are collecting stuff in it, and it's like the more you collect, the better your performance. It doesn't matter whether it came from this transmitter, that transmitter. So it allows you really to integrate the cloud with your system, because wherever you go, it's equally good. You don't have to keep your feedback with you.
Okay, well, with that, I'd like to present you, Dina, with this small token of our appreciation. It's a 60th anniversary AFOSR coin made just for this event. So with that, thank you very much.
Thank you very
much. We appreciate
much.
that.
Wow.
And let's thank Dina again for another very interesting talk.